Alright, so in today's lesson, we're going to look at measuring biodiversity using the Simpsons index. And so I know at the end, last time when we were talking about biodiversity, we had mentioned some of the reasons that biodiversity was important. So, a very diverse community is resistant to change. So if a natural disaster would occur or some sort of environmental change, a very biodiverse community would be able to resist that change and be able to deal with it a lot better than one that wasn't as diverse. So today we're going to look specifically about how we can quantitatively measure biodiversity, so like assign a number to it. Some things that we had mentioned before that are important to remember that have to do with biodiversity is species richness, species evenness, and how we're going to combine those two measures of diversity together to come up with is called the Simpson index of biodiversity. That's just the number we're going to use to represent how diverse a community is. So first, remember that species richness is a qualitative description. It only has to do with how many different species are in a given area. So, for example, if there is a section of forest that contained 5 different species of organisms, it would have a higher species richness than a similar sized chunk of forest that only had 3. It is more rich than the other. So just pure more number of species per unit area. But the problem with species richness is that more species does not always mean more biodiversity. Maybe take a second to think about why not. All right, because there may not be many individuals of each species. They might not be equally distributed. You might have 5 different species in that given chunk of forest, but 90% of the species that you find there are all of type 1. Right, 5 different species, maybe 90% of the individuals are all of the same species. You can't necessarily say that is incredibly diverse, right? So, species richness doesn't tell the whole story about biodiversity. It is not enough just to measure species richness. The other possibility is you could measure species or biodiversity by species evenness, which is a quantitative measure. It is a measurement of what is the abundance of each individual for each species. So, as an example, if I have that same chunk of forest with 5 species, if I have 20 of each of those 5 species to make up 100, right? That is a very even community. It has a high species evenness. Each of those 5 species are about equally represented. Now, if I had, I don't know, 20 of species 1 and then 5 each of species 2, 3, 4, and 5, that would be far less even and have a far lower species evenness score. When we're talking about biodiversity, both species richness and species evenness matters. So we say if there is a community that has a increased species richness and an increased species evenness, then it is by definition has an increased biodiversity. So we need to measure biodiversity by weighing both of these factors. So as an example, what if we had 2 fields, field A and field B, that contain these 6 species in each? Both fields have a total of 100 individuals, and the abundance of each species in each field are represented by these numbers. Which field shows the most biodiversity? That's the question we want to ask. Well, both fields have 6 different species, so as far as species richness, they're equal. However, field B has a greater evenness score because they are more equally distributed. So B then is more diverse. In this case, it was pretty easy to figure out which one showed the greatest biodiversity because we could tell just by looking at these numbers. However, in every single case, that's not going to be possible. That's why we have what's called the Simpsons Diversity Index, which is a numerical way, a quantitative way to compare different habitats and figure out which one is more diverse with a quantitative measure. So Simpson's Diversity Index, which is capital D or capital D with a little subscript s, is a measure of biodiversity that takes into account both richness and evenness. So the Simpsons index is going to be between 0 and 1. A high value of D, so like 0.99999, closer to 1, is good, and it means that the habitat is very diverse. It's very species rich and it's able to withstand environmental impacts. A low value of D, like 0.11111 or close to 0, is poor. And that means that the habitat has low species diversity, isn't very rich, and small changes to the environment could have serious impacts. So this is right here. This is Simpson's index equation, how to figure out the Simpson's index. Now it looks complex, but it isn't really that bad. There's only 2 variables, lowercase n, which is the number of individuals from each species. So if I find 5 white-tailed deer, that would be 5. And n is the total number of individuals of all species combined. Right, and so we're going to see how to use this to compute Simpson's index D. So let's calculate Simpson's diversity index for this same field. Remember, just based on our qualitative observations, we said that this field D was more diverse. So after our calculations, it should have a high diversity index, and field A should have a lower diversity index. This is kind of our prediction, what we think should happen based on what we've already said and what we know about Simpson's diversity index. So let's compute the two and figure if that's the case. All right, so first thing I'm going to do is figure out this part, which is in the numerator of my quotient here. The sum of the quantity n times the quantity n minus 1. So here are the number of each species, n, lowercase n, and here is the total, 100, uppercase n. So if I do for each species the number 57 times that same number minus 1, 56, I wrote them all down here. And then, summation, I added them all up. So 4,208 is this numerator right here. Pretty simple, actually. Just looking at this number and then multiplying it by 1 minus this number. 57 times 56, 32 times 31, 3 times 2, 4 times 3, adding them all up. Right. So next I'm going to figure out the denominator. Well, in this case, the total number, capital N, is 100. So 100 times 100 minus 1, 99, is 9,900. and that becomes the denominator. So here I have the numerator, and here I have the denominator. So the first step is to divide those two. And when you get that quotient, I take 1 minus that quotient. So in this case, for field A, my Simpson's diversity index is 0.575. I know I've done this correctly because this number isn't negative, it'll never be negative, and it's between 0 and 1. All right, so now we'll do the same thing for field B. So here again, I wrote down the numerator of the expression right here. 38 times 37, 16 times 15, 14 times 13, 22 times 21, 5 times 4, 5 times 4, add them all up right here. Now remember, this is still going to be 9,900 because the total for each is still the same, 100. So I took 9,900, put it in the denominator, and 1 minus that quotient, and I get a diversity index of 0.764. Again, I know that's correct because it's not negative and it's between 0 and 1. So let's compare the two. For field A, remember I got a diversity index of 0.575, or sorry, a diversity of 0.575, yeah. And B, I got a diversity index of 0.764. This makes sense because I said before I did any calculations that B should be more diverse, and it does now have a higher diversity index. So field B has the higher diversity index, so it has more species richness and evenness combined, and it would be more resistant to environmental change or environmental damage. Also, one thing you can say is that if I pick two plants at random from field B, I would be more likely to get two plants of different species than if I did the same thing in field A. That's another thing that having a larger diversity index means. If you're going to grab two different plants at random, you're more likely those two plants are going to be of a different species if there's a higher diversity index than a lower one. So the work for today is mainly going to be about understanding and applying Simpson's diversity index. So that should be it.